we can check, sir. We are just co-panelists.
No, sir, it's not showing. After I will do the broadcast, then it will going to show.
अच्छा, okay.
I think एक तुम अभी 16:55 हुआ है, तो I think we can broadcast, sir, 5 minutes prior, and then we can start on time.
अपने लोग आगे गए। स्वप्निल सब लेकिन में रुक स्वप्निल।
हाँ।
It's not showing.
ब्यूटे सर नहीं आ रहे, तो उनका रोल कौन ले रहा है?
अच्छा, कौन नहीं आ रहे हैं?
स्वप्निल,
हाँ,
ड्यूटे सर नहीं आ रहे, पहले हाफ एन आवर नहीं आ रहे ड्यूटे सर।
हाँ ठीक है, उनका तो अभी उनको बात करना भी नहीं है ना, अभी नेक्स्ट नए फॉर्मेट में आई एम जस्ट इंट्रोड्यूसिंग देम एंड देन आई एम पासिंग ऑन टू द मॉडरेटर। मतलब नाउ यू विल बी इंट्रोड्यूसिंग द पैनलिस्ट,
यस,
एंड देन पैनल विल इंट्रोड्यूस द स्पीकर।
विनय गुप्ता सर को मैं पास ऑन करूंगा।
यस, करेक्ट,
ठीक है, मैं इंट्रोड्यूस करके तुझे दे दूंगा, बाद में तू विनय गुप्ता सर को ये इनवाइट कर देना।
ठीक है, ठीक है, ठीक, ओके ओके।
Let me only do the introduction of panelist.
ठीक है, ठीक, okay, done. So I think, sir, then we should broadcast because it's 57.
और 3 minutes रुक जाओ यार।
Okay, ठीक है, ठीक।
How does it matter?
तो अपनी देशभक्ति के ऊपर बोल।
दीपिका said that we can't even find out कि कितने लोग अभी वेटिंग हॉल में है ना? तो अगर 100 भी हो जाए तो हम लोग ब्रॉडकास्ट करके स्टार्ट कर सकते हैं, बिकॉज इनिशियल ये प्री चलता है, वो तो चलता रहेगा। रूही, इज देयर अ वे टू नो हाउ मेनी आर इन द वेटिंग हॉल? नो, ओनली व्हेन यू क्लिक।
हुज़ैफा साहब, कोई ऑप्शन 2 मिनट है आपके पास? कितने लोग लॉगिन करके वेट कर रहे हैं, कुछ जान सकते हैं?
पॉइंट ये है कि जैसे 100 हो जाए तो हम लोग शुरू कर दें ब्रॉडकास्ट और काम, आई मीन वेलकम शेलकम स्टार्ट कर दें।
नहीं, 5 बजे चालू कर देते हैं, अपने आप होते रहेंगे, 15 मिनट उसमें लगता ही है सर।
हाँ, यस, इसीलिए बेटर है
5 बजे चालू कर देंगे ब्रॉडकास्ट।
हाँ सर, 1 मिनट में चेक कर रहा हूँ कितने लोग लॉगिन किए।
अच्छा, चेक कर सकते हैं?
अच्छा,
हाँ, 1-2 मिनट सर में बताता हूँ।
हाँ, and among ourselves, if anyone's voice is not clear or signal is breaking, let us inform each other that there is a problem.
Yes, yes.
Yes, sir.
फिर थोड़ा हैंडी रखिए सब लोग, मतलब anything if you want to check that it will be easy.
Yeah.
I think we have started.
Mm-hmm. I mean, I don't mind. We can broadcast.
Can I do the broadcasting?
Yeah. Yes, I think go ahead now.
Okay, sir.
Good morning, everybody. Dr. Roy, good morning.
नमस्ते सर।
Morning.
Good evening, sir. sir. Good evening.
Namaste, Professor Tandon.
नमस्ते जी नमस्ते
Good
Good
evening.
afternoon, Tanu Sahab. Namaskar.
नमस्कार नमस्कार
R.K. Goyal.
तो
I think Deepika.
I'll start now.
Vinay sir, we have touched almost.
Yes. Goel sir, seeing you after, of course, almost a month. Namaskar.
Last special lecture.
Yeah. No. If you join, it's always good for us. Definitely.
I also get updated.
So Vinay sir,
Dr. Edmund, yes, certainly. Swapnil, please.
Deepika, please you start now.
Okay.
Hey.
Good evening, everyone. We welcome you all to IIB's lecture series. Today we have with us is Dr. Edmund Booth, who will be presenting on seismic design of bridges and structures. I may now request Madam Ruhi to guidelines.
Thank you, Deepika. Good evening, all. Before we start the event, I would like to read basic rules and guidelines for all the participants. All participants will remain on the mute mode during the lecture. Questions should be put in the question answer block. After the lecture by the speaker, questions will be replied by the speaker panelist. Subsequently, attendees can raise hand below the option below at screen. During questions, specific participants will be unmuted by the organizers. After a participant's question gets over, the participant should mute himself. Participant's video will not be displayed on the screen. Speaker, panelist can share screen. Now, I would like to introduce our Honorary Secretary, E.R. Swapnil Joshi, our host for the day. Swapnil Joshi, an intellect who possesses bachelor's in civil engineering and double post-graduation from United Kingdom and NICMAR with specialization in construction project management along with law graduation. He has wide exposure in developing systems, had developed expertise in the field of CPM combining technical and latest management tools such as Primavera, ESTA, Power Projects, Telos, etc. He initiated and developed a mobile application, Intento Projects, for daily monitoring and real-time data analysis of projects. With successful implementation of digitalized integrated approach and his expertise in project planning, BEAM, and advanced technologies, he is able to deliver the client's goal successfully. Swapnil has been awarded by Indian Institution of Bridge Engineers from the hands of Sri Nitin Gadkari in 2014. Now, I would like to hand over to our host. Thank you.
Thank you, Ruhi, for a quick introduction. Let me just, formally welcome all the participants for today's lecture series, special lecture series 5 on seismic design of bridges and structures by Dr. Booth. Let me now, after this formal introduction, let me just, start with the brief introduction of IIB. And Ruhi, can you just take me to the next slide, please?
Yes, sir.
Yeah. So, IIB is being founded, Indian Institution of Bridge Engineers is being founded by Sri Engineer MC Bide, Chief Engineer Indian Railways in 1989, with the aim to promote bridge engineering in the country. After side demise of Sri MC Bide on 7 July 2018, IIB strives to continue to promote bridge engineering with same enthusiasm and passion. IIB is the only professional body across the globe exclusively dealing with the bridges, which has a spread over 33 states and local centers with more than 7,000 strong members and 169 institutional members. IIB also has published more than 29,200 pages of technical literature and also holds an outstanding Bridges National Award competition on a frequent times. So with good the support of Mr. MC Bide, IIB has started and we are taking it forward to the next level. Yeah, Ruhi, can you go to the next, please? Next slide. So with this, I would like to introduce our Director General, Engineer Deepak Divte, who is a civil engineer from College of Engineering, 1970, passed out in 1974. Through 1975 UPSC exam, he has joined Indian Railways as a class 1 officer and retired as a principal chief engineer of Indian Railways in 2011. During his service, he has worked on many important railway projects, also occupied posts of principal chief engineer, North Eastern Railway and Southwest Railway. Director, he was a board member on Konkan Railway Corporation, chief engineer on Konkan Railway project, and also chief project manager for tunnels of Mumbai-Pune Expressway. And recently, he has worked on Mumbai Metro 3, 33.5 kilometer fully underground metro construction project as CGM. So we have a great support of our Director General in various initiatives. Now I'll introduce our President, Shri Vinay Gupta ji. And he's also a moderator of today's event. So he is a civil engineer from BITS Pilani, 1983 batch, and director and CEO of Mrs. Tunden Consultants Private Limited. His specialization is in bridges, flyovers, underground and elevated metro structures, precast building, 275 meter tall chimneys, etc. He is an active member of various code committees, BIS and IRC, including BIS and IRC. His contributions includes IRC SP65 for segmental bridges, IRC SP71 for precast pre-tension girder bridges, etc. He is a recipient of several awards from IEI, IBC, and UK IERI. He has been lecturing as guest faculty in various institutions as well as the organizations. Engineer Vinay Gupta is also an president of Indian Concrete Institute as well as our own Indian Institution of Bridge Engineers. So this is a brief introduction of our enthusiastic and very supportive president, with whose support all these lecture series are being, achieved a new height. So now let me introduce my colleague, Dr. Gopal Ray. So Gopal Ray is a PhD holder from IIT Bombay. His phenomenal level of prowess has enabled him to associate with several prestigious projects, including the Apsara Reactor, BARC, Mumbai Airport Bridge Strengthening of Mithi River, ASSC Hospital, etc. He is an honorary secretary of IIB, general secretary of Association of Structural Rehabilitation and Retrofitting, committee member of ISSC, BIS and ACI. He has delivered many presentations nationwide as well as at the international level. He is also a keynote speaker and author for 4 international conferences and more than 10 national conferences. Dr. Gopal Ray has published more than 100 papers in the journals. He has also been awarded for 50 manufacturing innovative leaders at World Innovative Congress Award 2019. Also in Dubai for 40 most influential leaders under 40 years 2017-18 by Asia One and many more. With this brief introduction, let me invite our Honorary Secretary Dr. Gopal Ray to formally introduce the today's panelists. Gopal, over to you.
Thank you, Swapnil. It's my pleasure, or it's my duty. Let me say that to introduce Professor Mahesh Tunden. Before I introduce, let me thanks to organizers to give me the opportunity to introduce Professor Tunden. Professor Mahesh Tunden, Managing Director of Tunden Consultant Private Limited, is an international expert in the field of structural engineering. Many of his structure designed by Professor Tunden and Tunden Consultants have been widely acclaimed and has been received recognition in India as well as internationally. He has been the development in new codes, path-breaking bridge technology suited to Indian condition. It includes pioneer work in the field of segmental construction, integral construction, accelerated bridge construction, long span bridge, and structure for metros, both viaducts and underground. His structure have been described by highly creative and futuristic, aesthetic, environmentally sensitive and innovative. He has been also accreditation of International P in India, and he is recipient of Distinguished Alumni Award from IIT Roorkee in 2018. under the AICT program. Indian National Academy of Engineering appointed him distinguished visiting professors at IITs at Kanpur, Roorkee, and Gandhinagar 2005 to 2015. Currently, he is continuing as a guest lecturer in IIT Gandhinagar. But in my own way of giving introduction in few lines about Professor Tandon, let me like it will go in Hindi. अगर मैं दो लाइनें कहूँ टंडन जी के लिए, टंडन साहब के लिए, प्रोफेसर टंडन जी के लिए, एक दिन आपके नाम का भी शोर होगा, एक दिन आपके नाम का भी शोर होगा, लोगों का वक्त आता है, प्रोफेसर टंडन का दौर होगा. तो with this note, I thanks Professor Tandon for becoming a panelist for the today's event. Sir, we have learned a lot of things from you, and you have helped us as a young comers. You have encouraged us, and really thank you very much. Over to Swapnil, you.
Thank you, Gopal. With the quick, I know, it's very difficult to, introduce Professor Tandon in this short span. But thank you very much for your brief introduction. Let me now formally invite our today's moderator, Engineer Vinay Gupta, to, take over the station forward. Yeah, Vinay sir.
Yeah, thank you, Swapnil, and thank you, Dr. Gopal Ray. I think it's a very good continuation of monsoon in Delhi. And we have a fantastic speaker. This is my second experience with him. The first experience with Dr. Edmund Booth was in 2008. When we met in Delhi, we met in Chennai, and a fantastic gentleman he is. And he is an ocean of knowledge, especially when it comes to earthquake engineering. And Dr. Booth has been spearheading the group of Eurocode 8. That is a code on earthquake design. And let me tell everybody that when it comes to earthquake engineering especially, it begins with general criteria, which is majorly, we call it for buildings. And everything else, like chimneys, industrial structures, water, overhead water tanks, or bridges, and they are all a derivative. They are all branches of this general engineering on earthquake side. So he's the one who has spearheaded this group, wherein they prepared the international code EC8 on general earthquake engineering, which is then derived into bridge engineering, what we are more interested in today. So I requested Dr. Booth to please say a few words and say a few more sort of descriptions on Edmund Booth, and he agreed to that. In fact, the overwhelming thing and the response from his family is that Mrs. Anna Booth is also with us today, and I'm sure she will not mind saying a few words later on, of course. Right now, let us go ahead with the technical part of it. Anyway, so a few words about Dr. Edmund Booth. He graduated from Cambridge. He worked for 25 years in various design offices and on site. Since 1995, that's 25 years ago, he has run his own consultancy in the UK. And mind you, he's also been a professor. He is specializing in seismic design, assessment, and code development that we all know. He has been a visiting professor at the University of Oxford, and he's a fellow of Royal Academy of Engineering, and currently lectures at Imperial College, London. In fact, our special invitee today, Mr. Viswanathan, when I spoke to him that Dr. Edmund Booth is coming and delivering a lecture, he immediately recollected of Imperial College of London. So Dr. Booth, it's a good sort of a recognition that people know you for. Now, Dr. Booth has written a textbook on earthquake engineering, that is seismic design practices for buildings, and now entering its 4th edition, and has published many papers on the subject in journals and at conferences. So we have a person internationally acclaimed, of international fame, and a person who's absolutely thorough with the knowledge on earthquake engineering, which I think none of us knows well or adequately. So we'll hear Dr. Booth, and Dr. Booth, please share your slides and kindly start on.
Good. Well, thank you very much for that introduction. Um, can you see me? Am I on the screen now? Yes, I am. Good, excellent. It's a great honour and pleasure to be addressing the Institute of Indian Bridge Engineers, and I'm sorry I'm not able to be physically with you in India, and that's a sadness. But anyway. So, without further ado, I will see if I've got the technology and the skills to share my screen with you. Does that work? Share. And now we press that one. Go on. No, that's not for some reason. Oh, well, I know why not. Of course, sorry. There we go. Okay. So what I'm going to talk about today is a broad introduction to earthquake engineering. I'm afraid it's not a hands-on how to do it in detail lecture. My main expertise, as Vina Gupta has told you, is actually in building structures rather than bridges. As a young man, I spent 5 years on site in the UK and abroad working on bridges, so I do know something about them. But my introduction and involvement in earthquake engineering didn't come till much later. In fact,
Dr. Booth, just an interruption. Can you please speak closer to the mic so that
yes,
it's a
certainly.
little bit more? Please.
Right.
Thank you so much.
How is that? Is that better? You know.
Yes, somewhat better.
Yes. Okay. So in 1982, I think it was, I changed from being a general structural civil engineer to becoming a specialist in earthquake engineering, and really that's what I've done ever since. There we go. No, what's happened now? I don't know what's happened. Hang on, sorry, technical problem. Right, there we go. Screen sharing. Some reason we're not advancing slides. No.
Dr. Booth, you're on the last slide, so I think you'll have to just go on.
Oh, I see. Sorry, I'm with you. Yeah, of course, I'm with you. Thank you. Okay, it's the same as the first one. Okay, here we go. There we are. That's me. You may wonder what an engineer based in one of the least seismic countries of the world can possibly tell you about earthquake engineering. Well, I have looked and visited numerous earthquakes during my career. The last one actually was 10 years ago in Haiti, Port-au-Prince, which suffered a devastating earthquake. And now I leave it to younger men. At the age of 72, I think it's better that way. I said younger men, I meant younger men and women, because very much women are part of the tribe of earthquake engineers now. Actually, England is not completely devoid of earthquakes. Let's see if we can get rid of that. Yeah, there we go. There was a late Victorian earthquake in 1884. I think it actually killed 2 people, not very many, but still caused a lot of destruction. And exactly 100 years later, when I just started on earthquake engineering, we had another big one in Wales. Big for us, but for you, not really. Perhaps really what we have to offer from the UK is a great deal of research, design expertise, and university involvement in earthquake engineering. This is the shaking table at Bristol University, one of the centres in the UK. Imperial College is certainly another one, a great centre of expertise in earthquake engineering. So to put the whole lot into context, here is very much an up-to-date map of how seismic hazard is distributed throughout the world. So the red and orange colours up here, the low frequency vibrations, are the high seismic hazard places, and the whites and blues are the low one. You can see not a lot to show in Britain, a lot more in India, of course. And here we are. I'm sorry that part of Bengal seems to have been truncated, but you can see that most of India is pretty blue, but where it's pushing into the Himalayas and pushing up the Himalayas, there's a lot more activity, and some of it very intense. Vinay mentioned my involvement in Eurocode 8, which has been long-standing. Let me just tell you what's happening, how it views seismic hazard. The code actually is going a very radical revision at the moment. That's nearly complete, and it divides seismic hazard into 4 separate zones. And I think you have something similar in India as well. But the low seismic hazard, the whites and the light blues, if you like, very low seismic hazard, you needn't worry about seismic design. Other considerations like wind loads and minimum robustness rules are quite sufficient to cover the hazard from earthquakes. The next step up is where you do actually need to consider seismic design, but all you need to do is to do probably a fairly simple check on the lateral forces that the earthquake is inducing, and very often they'll be less than minimum lateral load requirements or wind requirements. So that would apply, I guess, in the Eurocode 8 scheme of things to places like Mumbai, maybe Hyderabad. So some consideration, but really nothing particularly onerous. Then it's where you get into the medium that the difficulty starts, because not only do you have to do a check on the seismic forces, probably quite a sophisticated analysis, and because it's a higher level of seismicity, the forces are going to be higher, and so may well not be less than the wind forces. But you have to consider seismic detailing as well, and we'll say something a lot more about that later on in the talk. And then finally, the high seismic zone, and I guess Kashmir. Interestingly, I think, is that Goa there? But anyway, parts of the main part of the Indian Peninsula, and also where are we? There we go. Into Bengal as well. That would be where you have to take full considerations of seismic design. So that's this recent map produced by by GEM, the Global Earthquake Model, an international collaboration to map the whole world seismically. And you can see it's pretty similar to the zoning that I think is current in the Indian Seismic Code. Places like this and this, and on all the way along the Nepalese border, as where the Indian plate is shoving into the Himalayas, high seismic hazard. But elsewhere in the country, apart from Bhuj and the area around there, actually quite low. The only earthquake that I've actually been to visit in India was the Bhuj earthquake of 2001. fascinating earthquake, lot of destruction. I can't remember now how many people were killed, but a great deal of construction. Many thousands were killed, and many tens of thousands made homeless, and a huge economic impact. And whole villages built of this rather very weak construction were completely wiped out, with tragic loss of life. But it was not only the non-engineered construction that fared badly. Actually, so did reinforced concrete construction, recent reinforced concrete construction. When I first saw this building here, I thought it was a 3-story building, but it's not actually. It's a 6-story building which is toppled right over. And you can see that surviving that collapse would probably not have been possible. Interestingly enough, in the Bhuj area in Gujarat, the traditional masonry structures didn't fare too badly. This one you can see, obviously you wouldn't want to be standing underneath that block there in case it fell on your head, but the structure is still standing, is probably repairable, and that applied to quite a number of the wonderful historic buildings and heritage buildings that you have in Gujarat. Ahmedabad in the same earthquake was a long way from the epicenter, but actually was very
Dr. Booth, sorry, I'm interrupting once again.
Sure.
Some people are writing to me that the volume is not adequate. Are you using the microphone of the laptop?
I am, yes. I'm speaking right into it.
Okay. You mind sitting down so that you're closer to the microphone? Because people are writing to me, if you don't mind.
Thank you. Good idea. Okay.
Thank you so much, and I'm really sorry for this interruption again and again.
Yeah, no, sure. No, it's better that people can hear me. Is that better?
Yes, definitely better.
Oh, good. Okay, right. I know what to do now. So we're talking about the Bhuj earthquake of 2001 and the responsive structures in Ahmedabad, a long way from the epicenter, but still very destructive there. A lot of modern construction was very badly struck, and you can see the whole end of that building has just collapsed, fallen to the ground, again with loss of life. Interestingly enough, again, the wonderful heritage structure in the city was much less badly affected. This is a lovely building that has survived for hundreds of years, a number of earthquakes, barely a scratch on it. So my lecture actually is in 2 parts. I'm going to talk a little bit, a very basic introduction to the seismic response of structures, mainly in the context of building structures, but more generally than that. And then I'm going to go home specifically into bridge structures. So I'm going to say something very simplistic about dynamics, because if you don't understand about dynamics, you can't really understand about earthquake loading. So I'm sorry if people have familiarity with this, they'll find it very simple, but I hope for some of you it will be of interest. So now what I need to do is to go back to now hang on. I think probably what I'll do is stop the share. Yes, here we go. Can you now see me, please? Nobody's responding. I'll assume they can.
Yes, we can see you well.
You can see me well. Okay.
We can see you well.
I hope you can hear me as well. So this
Yes,
is a model which I've used for many years actually, which tells you all you need to know about earthquake dynamics in a simple sort of way. What it represents is three structures, probably building structures. So here is a 1 or 2 story building. Here is a medium-rise 6-story building like the one that fell over in Booth all those years ago, 20 years ago. And here is a skyscraper. And what you'll notice is that each has its own characteristic period of vibration, so that the 1 or 2 story building vibrates very quickly. It has a short period. The medium side, it's a bit slower, and the skyscraper just sways gently from right to left, much more slowly. That turns out to be absolutely crucial in earthquake terms. Now, compare earthquake loading with wind loading. Wind loading, you've got external forces on the building. The wind blows like that, and it pushes the building, the structure over. The magnitude of the force is not primarily dependent on the natural period of the building. It's only in rather special instances that you have to consider dynamics. If you're designing a building for wind or any sort of structure indeed. Earthquake's quite different. Where's the loading coming from? There's no external load at all. What's happening is that the ground's moving, and what is important is the speed of vibration, or the speed of movement of the period of movement of the ground in comparison to the natural period of the building. So if you've got a very slow earthquake motion, and that's possible, it's the tall building that really feels that, whereas the medium rise and the short rise don't really mind about it at all. And then you can guess what's going to happen next. There's a faster one, and it's the medium rise building that really suffers. And then this is harder to do, but I will try. If we've got a very fast earthquake motion, yeah, there we go. It's the little one that suffers, and the two big ones don't really mind at all. You may ask, well, how do I know what the speed of vibration of the soil is going to be? Say a little bit more about that, but basically it depends on the size of the earthquake. So the bigger the earthquake, the slower the movements are, but also crucially it depends on the ground that the structure is founded on. So if you're founded on rock, the movements are very quick, and if they're, because the rock is so stiff, if you're founded on very soft soils, the soft soils wobble much more slowly. So here's two crucial factors you have to take into account, which generally speaking you don't need to for wind engineering. First of all, the natural period of the building, and secondly, the nature of the soils on which the structure is founded. Right, moving on, I think we'll go on immediately with that. So share screen, share, and wait a minute, let's have a look. Let's go, hang on. Yeah, here we go. Okay, so probably most of you are familiar with these resonance charts for continuous vibrations, and what they show is the response of a simple structure, a mass spring damper system, which will have its own period of vibration, natural period of vibration. And they measure its response up here to an input ground motion. And you can see that if the structure is very floppy, what happens is that the ground moves underneath and the mass stays where it is. So for a large ratio of structural period to ground motion period, low response. By contrast, if the structure is very stiff, it just moves exactly in step with the ground and there's no amplification at all. But if the structural period of the mass matches that of the ground motion, then you get a huge increase in response. And the response is very sharply dependent on the level of damping, this dashpot here. So an undamped system, the response shoots off to, well, actually theoretically to infinity, but to something really large. Whereas if you've got 20% damping, you're going to reduce the response very greatly. In the context of buildings, how do we know what the structural period is? Well, very roughly, you can say multiply the number of stories by 0.1, or divide it by 10 if you like, that's easier, and you get the structural period. So a 1 second period building corresponds roughly to a 10-story building, or a 2-story building is 0.2 of a second, a 30-story building is 3 seconds. What about the damping levels? Well, in building structures, it would be of the order of 2 to 5%, something like that. Bridge structures, probably a bit less, mainly. Now, that previous, that previous slide isn't for an earthquake ground motion, it's for a continuous cyclical sinusoidal motion like that goes on forever. The sort of thing that you might have vibrations in a factory or something like that on a machine mount. The equivalent for an earthquake is a bit different, and it's what we call it is a response spectrum. It's similar in form in that for very stiff structures you get no amplification of the ground motion at all. For long period floppy structures, it detunes from the ground motions and you get a low response. But where the structural period matches that of the ground motions, then you get a large increase. And so for this particular earthquake, we're looking at a resonant period of about 0.3 of a second. So my rule of thumb suggests it's going to be most damaging to buildings of height, say 3 to 5 stories, that sort of thing. And 5% damping is traditionally taken as the sort of level of damping you would get in a building structure. Actually, there'd be quite a bit of damage associated with that, but that's an upper end. And it's trimmed it down a lot from 0%, but unlike the sorry, that's the wrong one. Unlike for the continuous motions where the 0% damping goes off to infinity, there isn't time during the earthquake for the response to get infinite. The earthquake may last for a minute or less. So it's a lot more than with 0% damping than it is for 5% damping, but it doesn't shoot off the graph. Oh, now when I've pressed the wrong button, there we go. Sorry. Go to, sorry. No, let's just go back. Home. Right, no, I've done the wrong thing again. Sorry. Okay, here we are. So I said that the foundation soils are a crucial aspect, not just for supporting the structure, but also on determining what sort of loads the structure is going to see in an earthquake, because the soils affect the period of vibration of the structure and hence how close the structure is to resonance with the forcing motions. And the classic case of that was Mexico City in 1985, my second big earthquake, which I investigated on site. Mexico City, as you may know, the center of it is built on a dried up lake bed with some quite deep, very soft clay soils, and it's surrounded by much harder material. There was a big earthquake in September 85 on the Pacific coast, about 300 or 400 kilometers from the city, and by the time the earthquake vibrations reached the edge of Mexico City, the level of vibration was actually quite low. So a peak ground acceleration of about 2%. So if you were a 15-story building, you'd see something of the order of 10 or 12%. But still, most modern, well-constructed buildings or other structures could easily cope with that. However, as you moved from the hard ground on the edge of the city to the center of the city, where you had these soft soils that wobbled, this is what happened. You got a massive increase in response. So here the period of vibration of these deep clay soils was about 2 seconds. So tall structures of say 20, 25 stories were very badly affected in that earthquake. Usually the influence of the soil is not quite as extreme as this, but it's still significant. So here is one of the tall structures in Mexico City which collapsed. It picked up the vibrations of the clay soils wobbling around underneath it, and it collapsed, as you can see. This is well known. It's been well known for, well, 35 years, I suppose, and before that, and well recognized in codes. This is the design spectra that you get, I think, in the Indian code, and you can see that the requirement for a rock site is both lower than for a soft soil type up here, and also the periods of vibration are moving towards the long period end. So that's dynamics. I want now to talk about ductile and non-ductile response, because again this is a very crucial feature of earthquake engineering that must be taken into account. So if I stop screen sharing and show you my second exhibit, I'm afraid this is very simplistic, but bear with me. Now let's have a look. Let's have a look. Is that better? You can't really see it. I hope you can see this
Yes, yes, you can see it. Yeah.
It's a bit of spaghetti, right? So it's quite flexible, and you bend it a bit and it's fine. The problem is, so you can imagine this as a building. Let's imagine it as a building, and the earthquake comes along and it waves around and it's fine. The problem is, if the earthquake suddenly gives a big bang, it breaks. The building collapses and everyone inside is killed. So that's a very brittle response. That's what you don't want in earthquakes. You want something to be able to absorb the shock from the earthquake. And so you'd imagine that something steel would be much better. And by and large, you'd be right. So here's a bit of wire, garden wire. Sorry, I didn't straighten it out. I should have done it. But anyway, here's a bit of wire. Again, quite flexible. The flexibility is not that much different from the spaghetti, but the difference is that if the earthquake gets a bit violent and bends it, look what's happened. The structure is bent, but it hasn't collapsed, and it will hopefully not kill anyone. Maybe you have to rebuild it, because you can't, if that was vertical, you wouldn't want to live in a building that looked like that, obviously. So you might have to pull it down and start again, but at least you preserved life. Right, share screen, see if I can do it better this time. Where are we? Share screen, and we want that. Yeah, there we go. Good. Okay. Right. So, how do you achieve ductility in structures? Well, reinforced concrete. There are two main strategies. In fact, the same applies to steel structures as well. But let's start with reinforced concrete. The detailing of the reinforcement is absolutely crucial to the ductility that you can achieve. So here's a column which has completely shattered in one part, but has been preserved in another up here. And what you can notice is that although it's the same main steel that's going through both parts of the column, the lateral reinforcement, the hoop reinforcement, is very widely spaced here, but very closely spaced here. So the addition of these closely spaced bars has converted rather brittle concrete into something that can sustain a lot of earthquake shock. So that's the first thing. It's the detailing of the reinforcement, and we'll come back to that again in the context of bridges. The second thing is, if the structure is pushed beyond its elastic limit by an earthquake, you want to be able to control where the plasticity and the yielding occurs within the structure. So this is the classic diagram for building structures. What you want to achieve is plastic hinges occurring at the end of beams and not in the columns. How do you do that? You make very strong columns and relatively much weaker beams. So here's a strong column, weak beam. It's got good ductility. Weak column, strong beam, poor ductility. Why are columns so much less ductile? Well, because they're already under a lot of compression just from the vertical loads they have to carry, and concrete crushes in compression. So any additional demand from the earthquake is going to be much more likely to smash it. By contrast, beams, of course, are not compression structures. Basically, they're bending structures, and it's much easier to achieve good ductility in a beam. Right, so just an example from Turkey, in fact, in 1992. Here's a concrete frame which has a classic, what's called a soft story. So the upper stories are filled with brick. The lower stories are open. This is an unfinished building which was going to be shopping, so they left the bottom open so people could see what was happening in the shop. But when the earthquake came along, of course, the top didn't want to move, but the ground story was very flexible, and all the movement occurred there. And you can see what happened. If you look at that joint there, you can see this building was actually on the verge of collapse. And in fact, 3 very similar buildings next door had collapsed. Say a little bit about steel structures. Steel structures actually are not immune from earthquake damage. Mexico City, this tall steel building here, was one of the first major steel buildings to collapse, and it caused a bit of a rethink among earthquake engineers. Just merely ensuring that you were built in steel didn't necessarily protect you. And then it got worse, because in California in 1994, there were another very disturbing series of failures in steel structures. Here is the typical construction detail of steel moment frames in California, permitted by the code. This joint is entirely code compliant. It's being tested in the laboratory. It's been tested and it looks all right at first sight, but if you look down there, you can see what's happening. A big fatigue crack has started to form. So steel is not immune from earthquake resistance, and yeah, it's easier to achieve in most cases good ductility in steel structures for a number of reasons, but you can't take it for granted. I think I'm going to skip that slide. Just to say, ductility. What is ductility? Well, here is a simple diagram of the load deflection diagram of a simple elastoplastic system, and it behaves linearly up to a certain point, and at a deflection uy it yields, and then it stretches out like this, and at an ultimate deflection it breaks, it fractures. And a simple definition, numerical definition of ductility, is the ratio of that ultimate deflection to the yield deflection, and the greater that ratio, the more it can go into the plastic region, the greater the ductility. And if you do the maths on it, you find that having high ductility reduces response like anything. And so here is a response spectrum for a series of structures. One has a mu of 1. In other words, you can't let it yield. You can't let it go into the plastic region, because otherwise it would fracture. And this blue one at the bottom, you can allow it to achieve a ductility of 4. So this structure here can sustain deflections up to 4 times yield quite safely. And you can see there's a massive reduction in response. Actually, the reduction is roughly equal to 4, which is rather convenient. So if you divide the elastic response by the the ductility ratio, then you get an idea of what sort of seismic forces you have to design for. Of course, it's not just designing for the seismic forces. In order to achieve that large ductility, you have to do the detailing and the choice of yielding mechanisms which will allow you to sustain that very large plastic response. And I think this chart has actually been superseded. You'll correct me later, but the R factor in codes is essentially the mu factor, the ductility ratio. So this is what you can divide the elastic response by. If you go for ductile detailing, this is what you have to go for if you don't, and there is a reduction. If you don't have ductile detailing, then the reduction in force that you can allow is much less. And it's interesting that this type of no ductile detailing is only allowed in fairly moderate seismic zones in the Indian code. Right, I've talked a lot about mainly building structures. Now here's something about bridges. And can I go on for another 15 minutes? I think it'll take about that. Is that okay? I'll take silence.
Yes, I think 15 minutes is fine.
Yeah, okay, right.
We have time, no problem.
So, ductile and non-ductile response, we've talked about that, and it still applies to bridges. Yeah, here we are. That's not a very ductile response, I think you can agree. It's a bridge in California which was essentially destroyed by the Northridge earthquake. And you can see that although there's masses of vertical main steel in this bridge column, there's not sufficient lateral steel to stop those bars from bursting out and the concrete from crushing inside. An earlier earthquake in California, exactly the same thing happened. This was the famous two-decker Cypress Street viaduct in San Francisco. It was a pre-stressed, very brittle construction. A lot of brittleness in these columns, and they just completely failed. And the top deck came crashing down onto the bottom deck, and quite a number of people were killed. The Japanese have always been, well, up to the time of 1994 or 5, have always been a little bit suspicious of ductility as a strategy for reducing the strength of structures. So they've tended to go for low ductility and massive structures. And this is what happened in Kobe in Japan in 1995. I'm sure you've all seen photographs of the Hanshin viaduct. Massive columns, absolutely massive columns. But look what's happened at the base. Classic non-ductile failure. So the Japanese had a severe shock then. They thought the great strength would protect them in an earthquake, and Kobe taught them that that wasn't going to happen. So ductility and brittleness, still things you have to consider, not just in buildings, but also in bridges as well. Liquefaction. Liquefaction is where the soil loses its strength during an earthquake, and that's a huge problem for bridges. This is the Philippines in 1990, a river bridge, and it's not the structure that's failed actually, it's the foundations, and this bridge is now completely impassable. And here we are from same bridge, ground level. oh, that's got left out. Never mind. What causes liquefaction? Well, here's a simple diagram. It happens in granular soils contained of separate particles. You can think of these as grains of sand, which are surrounded by water, so it's below the water table, and which are rather loosely packed. And under the action of cyclic shearing, of horizontal movements, first one way and then another, this soil tries to compact. But the problem is that there's water in the way. So the pore water pressure rises, the particles get pushed apart. When they get pushed apart, they lose the frictional shear resistance that's being relied on to support structures. So it's the loss of strength is because under the action of this pore water pressure rise, the interparticulate friction is lost or severely reduced, and hence the shear strength of the soil in a similar way is severely reduced. Just to go through briefly the 4 conditions necessary for liquefaction to occur. You've got to have a soil which tends to densify under cyclic shearing. Excuse me, I'm just going to get some water. Right. Thank you, Anna, for producing that water. The soil, so loosely packed soils, loosely deposited soils, particularly prone to liquefaction. And secondly, you've got to have water. Dry soils do not liquefy. These two suggest that marine structures, river bridges, crossing rivers, particularly prone to this sort of liquefaction failure, because the river means you've got water, and the soils may well have been laid down rather loosely over many decades. So you may well have a rather loose soil which will be particularly prone to liquefaction. 2 more things. You've got to have a soil which derives at least some of its shear strength from friction between the soil particles, because that's the mechanism of failure. It's the loss of that friction that causes the loss of strength. So it's sands and sands which particularly prone to liquefaction. Clay soils don't rely on interparticulate friction, so they don't liquefy. And the 4th one is you need something to prevent these excess pore water pressures from draining away very quickly. What might prevent that? Well, what might promote the drainage, the free drainage of the soil? If you've got a large soil particles, if you've got a gravel, then there are large spaces between the gravel, so even if it does want to compact a bit, the water can move out very freely, and the pore water pressures won't build up. So generally speaking, it's only fine to medium fine sands that are prone to liquefaction. And the other circumstance in which you might, which promotes liquefaction, is if you've got soil layers which alternate between impervious layers and free draining layers. So if you've got a layer of loose soil sandwiched between 2 clay layers, the clay layers are going to restrict the dissipation of the pore water pressures and promote liquefaction in an even more dramatic way. And well, how do you know whether you've got liquefaction? Obviously you go through that checklist and just think whether it's possible or not. the Seed and Idris, some 30 years ago, worked out the basic method which is still used, and it's in, I see, the Indian code. It's quite complicated. This is a simplified procedure, and the technology and the information is developing all the time. If you're interested in the subject, I would commend you to have a look at the latest provisions in the Eurocode, because they've been updated a lot during the current revision. Right, so we've talked about brittleness and ductile behavior. We've talked about liquefaction and loss of support. Fault rupture. Well now, here is it's a dam. It's not a bridge, it's a dam which crosses the main fault that caused the Chi-Chi earthquake in Taiwan in 1999, and this is where you can see where the fault went through, and the fault displacement vertically was a massive 9 meters. So this is not, fault displacement is generally not too much of a worry for building structures, because they've got a small, relatively small ground footprint. But if you've got a long linear structure like a dam, or indeed a bridge, it is going to be very prone to that. So where you're crossing a fault, and this bridge did, unless you take some very careful measures, you're going to risk this sort of thing happening. Interestingly enough, in the Kobe earthquake, the Akashi Kaikyo bridge, which I think is no longer the longest in the world, but it certainly was at that stage, crossed the main causative fault, and the two main piers moved something like several meters apart horizontally. It had actually been considered in design, and it wasn't a problem because the structure is so long that it's fairly flexible, and a relative movement of a couple of meters between the piers in terms of strain is really quite small, and there was no damage to the bridge at all. It's still standing, and so that was a success in Kobe. And the final one I want to talk about is loss of decks on bridge bearings. And this is the classic photograph from the 1981 San Fernando earthquake, when suddenly it became rather obvious what the problem would be. The States had embarked on a massive highway building program in the 60s and 70s, and built a lot of these overpasses consisting of separately supported concrete spans on bridge piers. The earthquake came along, and you can see it just chucked the bridge spans off their supports. This is, of course, very well known in bridge seismic engineers. It was interesting, when I was in Port-au-Prince in Haiti, there were no sophisticated bridges like the ones we've seen up to now. This is just a very simple concrete bridge. The designer, I think, had been aware of this problem of restraining the bridge piers, the bridge spans, the decking, and had provided some shear keys like this, which had actually, interestingly enough, failed. But they had done their job. They'd stopped this deck from leaving the bridge, and the bridge was still passable and available to get emergency supplies across this river to where they were needed. And this is a detail. It's not my field, but actually preventing the bridge deck from leaving its support is not rocket science, really. You just need to hold it in place. This sort of steel cable restraint, I think, was the preferred method in the States, certainly up to a few years ago. But there are lots of other ways you can do it, and it's not that expensive. It's pretty simple stuff, but it works. Finally, I'm gonna say a few words about smart technologies for bridges. Now, I'm going to talk about two. Here we are back to this response spectrum. The two technologies I want to talk about are base isolation and supplemental damping. Base isolation makes a structure which is actually got a natural period of 0.3 seconds. I think it's really got a natural period of 2 seconds, and so detunes from response. Supplemental damping is increasing the level of damping, so dropping the response right away down to this green line here. And both apply well to bridges. I'm going to show a building to start off with, and this is the classic illustration. Here's a fixed base structure. It's been shaken about all over the place. The accelerations increase as you go to the roof, so things mounted on the roof are particularly badly damaged. Not only it's the structure that's damaged, but everything else inside is thrown around. Mount the building on resilient isolation bearings, and essentially the ground moves underneath it, and the building stays where it is. The roof structures are okay, and not just the structure, but the building contents are undamaged. A hugely successful technology, actually developed in its modern form in New Zealand in the 1970s, and adopted all over the world. I believe now that all Japanese hospitals are built as seismically isolated buildings, and I think most of the ones in the States as well. Well, in California and seismic areas of the States. Well, perfect for bridges, of course, because bridges often have bearings anyway. So you just need to tweak the bearings a bit. They need to be a bit bigger and a bit more flexible, but you've got a perfect way of isolating the bridge deck from the substructure. It's just the same principle. And adding damping, again, here's an example from a building, but what you do is you have a viscous damper, an oil damper like this, like the sort of thing that's in your car, which absorbs the shock of the road in a car, and you put it into the bracing system of the building, and then as the earthquake shakes around, instead of damaging the structure, it's moving these dampers in and out and dissipating energy and increasing the damping and reducing the response. And this is a photograph I took in San Francisco in 2016. It's the west abutment of the Bay Bridge, not the San Francisco, not the Golden Gate Bridge, but the Bay Bridge. Massive bridge, badly damaged in the Northridge earthquake of 1994 and retrofitted. And what they did was, you can see if you look up there, they introduced these big dampers. They did lots of other things as well, but one of the things they did was to introduce these big dampers so that when the bridge deck was being shaken around relative to the abutment by the earthquake, these dampers worked in and out and damped down the motion. So highly effective. Right, and well recognized in the Indian code. I'm pleased to say there's a lot in Eurocode 8 Part 2 as well, particularly in the new edition about these technologies. So there's lots of sources there. Right, further reading. Well, I've got to start with my book, haven't I? As now a retired engineer, I've handed over the principal editorship to a younger engineer, Damien, who I've known for many years. He's a rising star in Arab, the major consultancy. Perhaps he'll be running it in 10 years' time, I don't know. But anyway, he's done the main work of revising the 3rd edition to the 4th edition, and it's pretty much there. It's actually in press at the moment. They hope to get it out by Christmas. But that is for buildings. But we talk a lot about other aspects too. The specifically bridge textbooks that I know is Priestley, Seibel, and Chaldea. I knew Priestley quite well, and sadly died now. John Micheli, Chaldea also I know. Seibel not so well, but it's a very good book. But it is 24 years old, so not smack up to date. A much more recent book, again, I know Andreas Kapos and Nurai Aydinolu quite well. I don't know the other two authors. I think that's probably a more academic book, but I'm not really quite so familiar with it. Right, I finished. So I will stop my screen share.
Great. Thank you so much, Dr. Booth. It was fantastic listening to you after 12 years, 12 full years, I must say. So friends, first of all, we talk of industry-academia interaction, and I'm sure there must be several people from academics here, from colleges and all that. And of course, there are many from industry that I know. Dr. Edmund Booth has a fantastic combination of both these. Whereas in India, Dr. Booth, we have, those institutes where the professors teach, which is more or less fully academia. And then they invite some of the industry people like us, you maybe, and they have lectures and they call it industry-academia interaction. In fact, Professor Tunden also was very active with IIT Kanpur and also IIT Gandhinagar now. So this, I think the whole combination is the one. So it's two in one personality we have in front of us. And you started very well, and you gave us a good news or bad news, that EC8 is undergoing a radical change, he said, which I made a note of, and I hope you are able to catch up with those radical changes. And good, you started with Indian projects, you started with Indian cities. So you started Indian structures, monumental structures that gave us some kind of a feel that UK has heart for India. Right. So, and of course, I'm glad you talked about liquefaction, which is a favorite topic of the panelist, Professor Mahesh Tandon. He is known and recognized for this topic. And then, of course, you talked of seismic devices, wherein we are preparing and we've been preparing the code. And I am, of course, doing a lot of work on seismic devices from Indian standards, not from your standards, honestly. So that's very good to hear that we are all at the same wavelength. Of course, many people were making complaints to me about the volume, but I'm sure it's a topic that you have to concentrate on anyway. There's no choice. You cannot be playing music and then listening to this lecture. And friends, we are glad to have Mrs. Anna Booth with us. And if she's listening to me, would she like to come on mic and say a few words about her privileged husband? Because we know that behind every successful man, usually and normally and always, there's a woman. Like we say, behind Professor Tandon, we have Ranjana. I mean, behind Mahesh, we say Ranjana. So behind Edmund, we have Anna. Yes, Anna, we can see you.
Yeah. I'll just say how much I enjoyed that lecture. It's a privilege to be married to Edmund. I'm very aware of. I have been married to him now for just over 10 years, coming up 11 years actually. And during that time, it's been a real privilege to be there for him and with him, beside him. And I've really enjoyed participating in this event today. So thank you very much for having me along.
So next time we want to take you to Taj Mahal, which Edmund didn't take you, I think.
I look forward to it very much.
Yes, me too. So good. Thank you so much. So before I invite the panelist, Professor Mahesh Tandon, we also have a special invitee, Mr. T. Viswanathan, and I'm sure Mr. Edmund Booth is known to Mr. Viswanathan. So Mr. Viswanathan, would you like to give any kind of a commentary on Mr. Edmund Booth's presentation today? And organizers, please put this on spotlight view so that we see the speaker.
Yes, sir.
So Mr. Viswanathan, are you with us? You have to probably unmute yourself if you have not done so.
Trying to do that. Yeah, I got it now.
Yes, we can hear you well. Yeah.
Yes, actually, I think I went with Mr. Booth first time in Chennai, maybe some 15 years back. If he remembers it correct, he came along with Professor Narayanan and then the royal family. That's the first time I met. Then second time, he came on behalf of ICI. That time he was about to be married, so he wanted to rush back to UK. Now third time, at least I am able to see him on the screen and talk to him. Now I am happy that he is told that EC8 is completely changing. Is it EC8 part 1 is changing or part 2 is also changing? That is my question.
Right.
And
I'll answer that now. No, all 6 parts are changing, and the changes to all of them are quite radical, actually. So yes, that's my answer. Not just general and bridges and buildings, but towers and masts, chimneys and towers, and also big changes in the geotechnical the foundations part, which was part 5.
Good. Nice.
So I think before we have a question answer session, which I'm sure everybody, including me, are eager to come to, let us have some expert comments from Professor Mahesh Tandon, who has worked a lot on earthquake engineering, and he's a panelist today. And before he says a few things beyond my own level, I must tell Dr. Booth that in India, we have been using some of those seismic devices, which includes seismic isolators, that is rubber isolators. It includes STUs in certain bridges we have utilized. It includes friction pendulum dampers for certain buildings and few others. So we are using it, but in a primitive way, I would say. So over to Professor Tandon, please.
Okay. Thank you, Vinay. And I hope you can hear me.
Yes, that's right.
Hello?
Yes, you're perfectly audible.
Okay. Okay, thank you very much. So first, I'd like to say that Dr. Booth has very modestly called his lecture today Introduction to Earthquake Engineering. I would like to say that it is always a pleasure to hear an expert simplify the most complicated things. I think an earthquake engineering is a subject in which this is most essential. I too had the privilege of hearing Dr. Edmund Booth when he was much younger, maybe 10, 12 years ago. Same place in Chennai and in Delhi. And at that time, the the EC8 code was one of the subjects. Of course, we had a series of lectures on Eurocodes. And as far as earthquake effects on buildings is concerned, that little course, short one, was taken by Dr. Edmund Booth. And I still remember parts of it. I just wanted to mention that Eurocode 8, as it is known, EC8, it not only covers new buildings, but it also covers existing buildings, their assessment and retrofitting. Of course, one of the questions that I would like Dr. Booth to please answer is that whatever modifications or improvements that the EC8 is undergoing, I hope that there will be something more on subjects like confined masonry, for example. There is not very much, except perhaps a few, one clause or something like that, which I remember, if I remember correctly, on confined masonry, because that is a subject which has suddenly taken on a lot of interest in the country, because a whole new campus at IIT Gandhinagar has been made in confined masonry. And of course, so far, there have been a few shocks here and there, not the big one. It seems to have behaved well, but we would like to know whether this is going to be covered in the revised EC8. I think if you ask me what is the most important takeaway as far as this lecture is concerned, apart from understanding the basics of earthquake engineering as applied to buildings and somewhat to bridges, I think one issue is that buildings, when they have a period of vibration which is similar or close to the period at which the ground is shaking, that's when you have the biggest effects. Now, one simple formula, which is also in our code, is that if you know the number of stories, you multiply that by 0.1 and you get roughly the period of vibration. Now, what I would like to add to whatever Dr. Booth has mentioned, talked about, is that rocks in general, I mean, that means hard rock I'm talking about, it can have a period of vibration. That means the ground shakes at a period of vibration at about half a second, 0.5 seconds. And if you have soft soil, it can have a period of vibration of 2.5 seconds. So you see the big range that the earthquake can really shake the ground in. And so if you know what type of soil you are on, you can also find out as to what is going to be the most susceptible buildings. It doesn't mean that you don't have to design for earthquakes, but it means that at least you know, as a thumb rule, what buildings in that area are going to be affected the most. And if you look at Delhi, for example, in Vasant Vihar, we have rock. In Noida, we have very soft soil. So you've got the whole range of type of strata in one single city. An example was given by Dr. Booth about Mexico City as to buildings which were outside the city and the buildings which were inside, which were actually founded on a kind of a retrieved lake. Those are the buildings which got most affected, because the period of vibration of the soil in that area was very close to 0.1 N. So it's that is the most important takeaway, if you ask me, that it is always better to get reminded of the fact that there are certain types of buildings in certain types of situations which will make them more susceptible. And unless you do, I gave you the example of Delhi, unless you do micro zonation, you will never know. If you say Delhi is in some earthquake zone, that is not enough because Delhi itself should be categorized in different zones so that we know what buildings are most susceptible in which area. One question that I have, apart from the one that I've already asked, which is about confined masonry, is if Dr. Booth can throw light on this subject. Of course, we have almost an embarrassment of the number of codes we have on bridge engineering in India. There are 3 codes. One is by the railways, one is for the highways, and one is by the Indian standards, which are the
BIS.
Bureau of Indian Standards. So there are 3 codes on bridges, and all of them say different things. Of course, that is an embarrassment which we'll one day or the other, I hope, we'll get over. But in one of the codes, which is applicable to highway bridges, that is the SP IRC SP 114, it says that if the response reduction factor is 1, response reduction factor is what you call the Q factor in Eurocode. It seems to suggest that there is no need to design or detail the bridge structure for ductility if you have designed the structure for response reduction factor of 1. I would like to get Dr. Booth's opinion on that subject. So that's all I have to say. And thank you so much, Dr. Booth, for taking the trouble and time to educate us on many new things and reminding us many of the old things that may have gone blank from memory. Thank you.
Yes.
Okay, so Dr. Booth, would you like to pass any comments or replies to Professor Tunden?
I'm sorry, I left. Well, I seemed to leave the screen, but I wanted a piece of paper to write your questions on, and I hope I've got them all. Taking them in turn. Absolutely right. Eurocode 8 had a part 3 on retrofit of buildings. It's now been considerably updated, and it now includes bridges as well. So Eurocode 8 does cover the retrofit not only of buildings but bridges too. I have to say that it's not a part I'm completely satisfied with. It's got a huge amount of very detailed and extremely useful technical information. I'm not sure if it's really the best way of doing practical retrofits, either for bridges or buildings. So that's my opinion. It's not going to change now. I think if I were doing a retrofit or indeed an inspection, I would not just use the Eurocode. I'd look at the New Zealand code as since Christchurch earthquake has been hugely reformed. They're very practical people, the New Zealanders. It's excellent. It's very good. And the Americans too, the Californians, have produced some very, very good codes. So there's American Society of Civil Engineers Standard 41, and definitely commend that to you. I have to say, I'd start with that rather than the Eurocode. The Eurocode's good, very good for detailed analysis, but I find it a bit academic, to be honest. So that's the first one. Oh, I just wanted to say that you bridge engineers, you've got a much easier job doing retrofit than building engineers have. It's a nightmare in a building because you don't know where the structure is. It's all covered up. Whereas on a bridge, you can see it. So I just wanted to say that. Okay, confined masonry. Yes, interestingly enough, it was quite widely used in Haiti, in Port-au-Prince, and it responded pretty well. And I think even more so in Chile, where it responded very well, much better construction, much better controlled. Yes, the whole of the clauses on masonry have been extensively revised in Eurocode 8, including the bits on confined masonry. It's not my particular expertise, but I think there's a big improvement there. So that's that. You were talking about how crucial the soils are. If you don't know what the soils are, forget it. Don't go somewhere else and apply your trade somewhere else if you're going to do an earthquake-resistant design. Absolutely right, Professor Tunden. Couldn't agree more. The way in which the soils affect the excitation and the calculation of it in Eurocode 8 again has been massively upgraded, and it's actually a bit more complicated now. You've got 3 separate methods, from a simple method to a very complex one, depending on the circumstances and the importance of the building. But I would certainly commend that to you as something to look at, because there's a lot of very good information there. The Alain Pecker, who led the project team for redrafting, is one of the leading seismic geotechnical engineers in the world, and I have huge respect for him. And then the final one was this thing about if you do an elastic design, if you take R equals 1, can you forget about seismic detailing? Well, that's very interesting. In a way, that's what brought down the Hanshin viaduct in Kobe. The Japanese were relying on great strength, essentially elastic response, and they hadn't detailed their columns properly. They thought they didn't need to. So, on the other hand, to go to the detail and expense and trouble of seismic detailing is considerable. It's not an easy thing to do, and it costs money and time and so on, and expertise too, not just for the designer, but also for the contractor. And it's no good having a wonderful design coming out of our design offices if the contractor can't understand it and can't build it. Anyway, the way that we're doing it in Eurocode 8 is saying, okay, if you go for lower, what we call Q factors, you call R factors, the Americans call R factors, you can cut back, as it were, on your seismic detailing, do hardly any seismic detailing at all, but you're not allowed to do that in areas of high seismicity. So that's only an option for moderate and low seismicity areas. So that's the way we've approached it. I don't know, does that answer your questions, Professor Tunden?
Yes, thank you, Dr. Booth. We have a question now from the other participants. Engineer Brian Hackaday, he's a very active member of the executive committee of IB. And of course, he's a very good engineer as a designer and constructor. His question is very simple. Question is, Dr. Booth, have you come across a failure because of the vertical acceleration in your vast experience?
This is a great puzzle to me. I think that I've always believed that vertical accelerations in earthquakes are much less important than horizontal ones. after all, just for our size, for our normal gravity design, we are designing for 1G, aren't we? We're designing for the full gravitational force, and then we put a factor of safety on it, so we're designing for something like 1.5G. Now, you can get 1.5G in an earthquake, it's true, but that's pretty unusual. Whereas lateral forces, they can be the same, they can be 20 or 30% of the weight in some circumstances. There's no way we're going to design for that level of force if we're not interested in earthquakes. So generally speaking, I think vertical accelerations are much less of a worry than horizontal ones. There are circumstances in which they might actually be rather important. I suspect, and Professor Tunden can comment on this, because I'm not a bridge engineer. I wouldn't describe myself as one. But for example, this business of the bridge spans being thrown off the supports, I suspect vertical as well as horizontal accelerations are rather important there. The same applies actually to masonry structures, which are like sandy soils. They rely for their shear strength on friction, and the friction is generated by gravity. So if you're suddenly accelerating downwards, you're losing that friction, and you're going to reduce the shear strength. But the academics love talking about this problem. It's an important one. I don't think there's ever been a really definitive answer on it, but that's my opinion anyway. Interesting to see what Professor Tunden has to say about it.
Well, I think we have something in our code about, which gives you pretty serious kind of provisions. It says that the vertical acceleration should be taken as 2/3 of the horizontal acceleration. But you see, in the vertical direction, especially in a bridge, you got a very low period of vibration. So if you have low period of vibration in the horizontal earthquake, where you would have a fairly long period of vibration, here it is totally different. In vertically, it's only the piers which are going to really go up and down, and the period of vibration is very, very small in that. So you are going to get fairly high stresses induced because of vertical acceleration. And as far as the superstructure is concerned, of course, it can totally change the equation. If you have a pre-stressed concrete structure, which is okay for vertical loads as they exist, but when you add to it the vertical acceleration, it may change the thing completely. I mean, you may have to, if you put too much pre-stressing, it may not be okay, because you may have crushing of concrete. And if you put too little, then again there is a problem. So I think both superstructure and substructure, but particularly the substructure, it has serious consequences of vertical acceleration, which people are often neglecting, which they should not neglect. And the period of vibration has to be calculated again, or you can just take it as the peak ground acceleration of whatever exists, which is 2.5 times what we call SA by G. I mean, that is the acceleration that you should take, and because the period of vibration is too low, and find out whether that affects your piers or not, and maybe piers and foundations both.
Okay, I have another interesting question coming in here. Very interesting, in fact. In bridges, we try to use weak column, strong beam concept. It is converse to that in the buildings, where we go for a strong column, weak beam concept regions. So I know Mr. Tunden can reply, but I want to hear this from
yes,
Dr.
yes.
Edmund Booth.
No, today we must get Dr. Booth's expertise on it, because we may not get that opportunity very often. You can hear me anytime you want.
Yes. So, Dr. Booth, what is your take on this?
No, I mean, I think it's fairly clear that to form a collapse mechanism in which the ductile hinges form within the beams is just not an option, and not a necessary option actually in bridges. And the obvious point that you want the collapse, the yielding mechanism to form is by the formation of plastic hinges at the base of the piers, and that's perfectly satisfactory. After all, most bridges are essentially just one-story portals, aren't they? They're not multi-story buildings like the one I showed in my slide, where completely different considerations apply. So that I'm quite comfortable about that, and in fact, if you know where the plastic mechanism is going to occur in the earthquake, and it's easy to ensure that that's at the base of your bridge pier, you can reinforce and detail it to sustain large deflections and large movements. And that's been, I think that's well proven, because the older bridges in California weren't well reinforced and detailed prior to about 94. In the last 25 years, they've had a massive program of strengthening the base of columns by confining them, and that's worked extremely well. It's been proved in earthquakes that this extra confinement at the base of columns, very easy to do, not that expensive, works very well indeed.
Yes. So, Dr. Booth, I think there is a single break. Okay. We have a question from one person, Mr. Rajiv Ahuja, who is a part of our code making committee along with most of us. His question is highly technical. It says, for a single pier of a bridge, response reduction factor Q should be a fixed value irrespective of its height and dimension, or should it be variable value related to the actual stiffness of the pier? So his question is, should the value of R or Q, in India we call it R, vary depending on the flexibility of the structure, that is height, dimensions and all that? So any views from your side?
Well, I'm not sure if that's the way I would have approached the problem in the first place. I think that if you're, for example, if you're considering a viaduct which is crossing a valley with a number of piers of varying length, clearly the stiffness, the lateral stiffness of the piers is going to be much greater. The flexibility is going to be much greater at the center of the valley, where the piers are longest, than it is towards the abutment, and that's going to affect actually the yielding mechanism in the bridge. It's going to affect where the plastic hinges are going to form and how they're going to spread among the structure. So it's not the primary consideration is how you ensure that where the plastic demand occurs, whether it's the base of columns, which it probably is, or elsewhere, the detailing at that point is sufficient to withstand the sort of plastic demand that the design earthquake is going to impose. So I think the problem with with Q factors and R factors is it's very easy to think, well, we do an elastic design and then we divide everything by a Q factor. Unfortunately, life is not nearly so simple as that, because once the structure yields, and it's the same for a bridge as it is for a building, the response departs very significantly from the elastic response. So that taking the elastic response and scaling everything down by an R factor only works if you've got well-distributed plasticity demand throughout the structure. And in my case of the viaduct crossing the valley, that's not going to happen. The demand initially, unless you take special measures, is going to occur in the short columns. And actually, just to say, the Nigel Priestley book, the textbook, is very good on that. Some excellent stuff on that, and he's got some. He and his colleagues have got some very good ideas.
So, Dr. Booth, we have about 30 other questions. I don't know how much time we have to take those questions, but out of 30, the 29 of them are that the presentation was excellent. You made complex problems very simple, and we are highly delighted and glad. So 29 are those. I'll read one last one, that's 30th question.
Okay, thank you.
The question is, details of response reduction factor R, or Q in your case, for superstructure is not considered in the table under IRC SP 114, as the same is to be designed to remain elastic, the structure, superstructure. But what should be the design seismic force, that is vertical direction, for stability checks of superstructure, particularly at very sharp horizontal curvatures, with Q as 1 as per the R value adopted for substructure? Let's say for Q adopted for substructure is 1. What should it be for the vertical, if I may understand rightly?
Oh, I see, yes. Well, I think most codes say that you're not allowed to invoke ductility for vertical response. And I think that it's the same actually in the revision to Eurocode 8. The current version says that. I think the American codes say something similar. I imagine the Indian code does as well. And the reason is that it's harder to develop the ductility in the vertical direction. So I'm quite comfortable with the idea that for the vertical direction you use a different R value than you do for the horizontal direction. I think that's well founded and sensible.
Right. So I think I must say that we had a fantastic questions and answers. But if you give 2 more hours, there will be 200 more questions, and certainly we can't take 200 more questions. So I think what we should do now is, Dr. Booth, in fact, our Director General, Mr. Devte, was supposed to say a few words, but he has not been able to join due to certain reasons. I don't know what. But I want to just inform you, I'm sure you may be aware, tomorrow we have 73rd Independence Day of India celebration. And for that reason, we preponed this lecture from tomorrow to today. Because of this complete holiday all over the country, Independence Day, and that's a national holiday which is observed everywhere, including markets, shops, everywhere. So just a few words about this Independence Day rather. My general feeling about, it's for everybody, not only for Dr. Booth. My general feeling about the engineers, especially in India, is the engineers have a low self-esteem. And this is because they're not very good communicators comparatively. When we talk of, say, management people or marketing people and all that, they are not able to express themselves very well. They may be doing wonders in terms of the actual work, but they do not know that they're doing wonders. And that's why they carry a low self-esteem, and they normally hide their faces while moving in public, in general, I'm trying to say. But if we talk of a civil engineer, or rather engineers in general, in my opinion, civil engineer builds the foundation of this world. So that's a beginning. Any structure, any inhabitation, you need civil engineering first. And then comes the mechanical engineer who puts a machinery, a system into this so-called foundation. The chemical engineer puts a process flow into the system. Electrical engineer puts energy into the system. And the computer engineer puts a planning, a program into the system for it to all start functioning. So when so many things are done by the engineers, why do we have to say that we are not as high as many others? Engineers are doing fantastic jobs, marvelous job. In fact, the transport minister, Union Transport Minister of India, Mr. Nitin Gadkari, he said that, look, I don't work, I only pass orders. It is you people, you engineers who work. You are the ones who are contributing to the development. I am only accepting or I am only ordering to you and passing the orders. So it is really the engineers who are the rightful people who should deserve or who deserve all the honor, all the respect, all the praise. So with these words, I must say that we all have a happy celebration of this Independence Day of India. And lastly, since our DG is still not available, I will request, we have two honorary secretaries, Mr. Swapnil Joshi, who you heard in the beginning, and Dr. Gopal Ray. Of course, let me just tell you a bit about them. Mr. Swapnil Joshi is more into project planning and implementation, and he works on Primavera, etc. He has developed his own cell phone apps, etc. for monitoring the project progress from anywhere, from remote control, from remote distance itself. And the other honorary secretary, Dr. Gopal Ray, he's an expert in what we don't like, is strengthening and retrofitting of structures once they are creating problems for us. And we don't want that to happen, but we need him like a doctor, and he's a doctor, Gopal Ray. So I'll request Dr. Gopal Ray, our honorary secretary, to say, propose a formal word of thanks to the fantastic evening we had today.
Thank you, sir. Thank you, President. जो culture है कि the vote of thanks should begin with some. I'm sorry, Dr. Booth. I don't know how to translate the shairi into Hindi shairi into English, so I will help you out. So let me thanks to you first of all for giving a fantastic, like, even when you are talking, our chairs and everything was steady, but your the all tools and everything were vibrating. So I was thinking, and I have written something. बिजी थे हम अपने डिजाइन ड्राइंग के करेक्शन में, बिजी थे हम अपने डिजाइन ड्राइंग के करेक्शन में, जरा सी धरती क्या हिली, डॉक्टर बूथ याद आ गए. तो मतलब
I think you must translate this for him, and he will remember it, I'm sure. And I hope Mrs. Anna Booth is also here, and she will also like to remember. Dr. Rai, I think it's fantastically worded. Please translate it.
Yeah, sir, translation thoda sa busy, like we all were busy in our design drawing correction. We all were busy in our design drawing correction. The little shake in earth remembered Dr. Booth.
So little shaking on the earth, of the earth, reminded us of Dr. Booth. What words, fantastic.
So this is just, I was sitting and I was monitoring that part. So I thought I will write, apart from retrofitting, there are less retrofitting projects. So I am focusing on little shairis on civil engineering and all. So this is the part-time assignment.
He's a very poetic person.
Thank you, sir. Let me give now my formal vote of thanks. Let me thanks to our today's speaker, Dr. Booth, Mrs. Booth, for really giving your valuable time. And the kind of first time I have seen demeanor in seminar, in webinar. Okay, this is a good combination. We thought physical meeting and seminars only we can see the instrument, tools, and everything. But this myth also you have overruled, that you can show the demeanors in the webinar. So this is first thing I have seen, that you are showing some tools and you are trying to more attract the audience and explaining like. So I think although you are steady, but you focus on the vibration structures, okay, or the shaken structure. So really your tools and everything. And thanks to Mrs. Anna Booth for encouraging and giving the support, and the structure will last for longer and much more longer, and it will be steady, and it is you are earthquake proof. I think that is the best part. So let me thanks to Dr. Vishwanathan for joining and briefing us and sharing some moments with today's speaker. Thanks to my mentor and everyone's like I have told in the beginning only, ये दौर जो है प्रोफेसर टंडन साहब का दौर है, ठीक है. And not only like we feel very like proud when we come across and he explained like again we have to come with a pencil and rubber, and he explained like that and he teaches like that. So we never like we learn every day with Professor Tandon. Thank you, Professor, for encouraging. एंड ये सच में ये जो सदी है, अगर ब्रिज में सिनोनिम्स डाली जाएगी तो प्रोफेसर टंडन वहां से एक सिनोनिम्स निकलेगा. थैंक यू प्रोफेसर टंडन फॉर एनकरेजिंग and helping us, and always IIB strong support for IIB strong support Professor Tandon. Thank you very much. Thanks to our Director General DG Dute. Because of some personal reason he could not join, but he has given a very good message. He has given thanks to the speaker and also to the eminent panelists and all the eminent the attendees for coming and joining. And today our score has been went to 3,450. In last 2 months, we have given a webinar and a lecture series. We have trained to 3,250 people. So this is a big achievement for the IIB only. Thanks to our president. All things like we are just what instruction and what decisions he take in a quick way. And our president engineer Vinay Gupta ji. This IIB is flourishing with one word, Vinay Gupta ji. Thank you very much for your strong support. To our treasurer, Mr. Kelkar, for always supporting and always trusting us. Then to our engineer, secretary engineer, Swapnil Joshi, who not only plans his projects well, he also plans the IIB events also. So all appreciation goes to Swapnil and his team. Deepika Singh is also from her team. Thank you, Deepika. And our coordinator, Ruhi Agarwal. I think we should, Ruhi and we should focus on them also. To Deepika, say, Deepika, can somebody focus to Deepika also? We should encourage, Deepika is a civil engineer. She's working with Swapnil and she's all the events. She trying to help IIB. And Ruhi Agrawal is a coordinator. Hi, Deepika. Thank you very much.
Thank you, sir.
Ruhi Agrawal, Ruhi, you can focus yourself. It is possible. Yeah. Thank you, Ruhi ji. And to our Huzefa ji, the webinar who has given all this webinar part in this. But as on the eve of independence, I request everyone to stand up for national anthem. And you will see in the video, what video I'm playing, the journey of from last 2 years when as a president, engineer Vinay Gupta has taken over as a president. And also we have designed some decorative balloon. So can you allow me to share?
Yes, please.
शुभ नामे जागे तब शुभ आशीष मांगे गावे तब जय गाथा जय हिंद।
Thank you.
Jai Hind.
And with this नेशनल एंथम एक छोटी सी अभी अभी लिखी हुई शायरी से मैं कंक्लूड करूंगा जो हमारे देश के लिए अर्पित होता है। और ये शायरी थोड़ी सी मैंने लिखते लिखते किया है। न एसिलरेशन मेरा है, न एसिलरेशन मेरा है, न अर्थक्वेक मेरा है, ठीक है, फिर भी मेरा ब्रिज डटा हुआ है, फिर भी मेरा ब्रिज डटा हुआ है। मुझे गर्व है, मुझे गर्व है इस छोटी सी बात का कि पुल हिंदुस्तान का है और ब्रिज इंजीनियर हमारा है। थैंक यू वेरी मच। विद दिस
Thank you.
you
Very good.
Nice. Very good.
thank you sir.
Right. Great.
This is just a balloon decoration of IIB logo.
In the tricolors.
Yes. Thank you, thank you.
So, Dr. Booth, I hope you enjoyed this evening.
Yeah, very much. Thank you. Yes, I did.
Thank you. Thank you so much.
Good.
Thanks to everybody.
Jai Hind sir.
Thank
Bye.
you. Jai Hind. Jai Hind.
Bye-bye.
Hey Preeti,